Hello, it's time to get started. Hope you don't mind that. Have a seat, Smita, please. Okay, I was asked to have the pleasure to introduce Chieh, who was a student here a few years ago.
A few years ago.
He graduated in 2007, I think. He worked here with Paul Goldbart and also with Paul Quudits. So he seemed to have a specialty with Pauls in particular. And I think with Smith as well, and various other people here. He was one of the first students here to get entangled. And as far as I can see, he hasn't managed to get disentangled. So after he left, he went to, I think, to Waterloo, to the HUC, and then he broke an important barrier when he moved to Stony Brook. He was the first person with a condensed matter type background to be admitted at the C.N. Young Institute for Theoretical Physics. There was a no for a very long time until Young changed his mind. Okay, so he's going to tell us today about his recent work you can see the title here. I'm not going to repeat that for you. And he's going to be here for the rest of the day, okay?
Thank you. Thank you, Eduardo, for very nice introductions. So it's really good pleasure for me to be here. It's like homecoming and see quite a few familiar faces and also a lot more new faces. So just want to say, interrupt me if you have any questions. So yeah, so today I'm going to tell you about a recent work that I did with my students. And I need to find a place to stand properly. Yeah. Laser, okay, need to turn it on. This is I work with my student posted in the archive, Hong Yu. And this is about a study on time crystals. And you may ask, since time crystal has been proposed and discovered or even implemented on various platforms, and is there anything new? At that time, we were actually thinking not so ambitious. We are looking at a model we could, for example, realize this on some cloud platform of quantum computers that could implement a period tripling instead of doubling. We were just naively thinking about a model. And as my student dug into more, and we found something more interesting, and we can generalize a time crystal that breaks translation invariance in time to n periods. And then we ask about transition between them. And we found something interesting is that we have a phase between two time crystals, which are both thermalized and also exhibit spontaneous symmetry breaking in discrete time translation. But the thermalization happened in subspaces. So that's why we have the title called Subspace-thermal discrete time crystal. So, but I will explain to you how we came with this. Yeah. Okay. So feel free to stop me. Should point this direction. Yes. No. No, the cursor is at the other. So usually with Zoom, you have to press your cursor on the, yeah. Okay, so let me just review. We all know crystals, so special crystals. And this nice picture here. It breaks spatial translation, continuous translation, like spontaneously. So presumably there's some Hamiltonian, it's translation variant, and we see the crystal every day, right? And so this comes from the order and disorder. These ideas in physics actually involve a lot of interesting phenomena, right? For example, not just the time crystal, the spatial crystal. You could have, for example, here, atomic gas, BEC, metal, superconductors, for example, ferromagnetic phase and parametric phase. These are order and disorder. It happened everywhere in physics. So maybe let's go back a little bit earlier in the history to look at who actually think about the space crystal, the ordering. So it actually started quite early. You see in 1611, Kepler actually conjectured maybe the FCC is the densest structure for 3 spatial dimensions. And it actually was Gauss, maybe after more than 200 years, to prove that FCC is indeed the densest, but among lattices, regular lattices. And it took up more, I think, 170 years to actually prove this conjecture by Kepler is correct. This proof would involve considering not just the lattices, but everything. So this is thing that to prove this is really non-trivial, although we believe that it's true. So a lot of things that we believe is true is really difficult to prove. So now you look at the ordering, spatial ordering. For example, there is a negative result. By Merman, it proved that there's no crystalline order in 1 and 2 dimensions for non-zero temperature. So kind of negative result. So, and how about 3 dimension? Actually, we don't have a rigorous proof of existence of crystalline order, despite we have the real stuff there. And this is the table taken from my colleague, Ben McCrory, Advanced Statistical Mechanics. And he, in his book, he put down a wish list, the missing theorem that he wished somebody could prove it. The first on the list is existence of crystalline order for D equals 3. There are other wish lists, for example, existence of fermatic order in quantum-Heisenberg model for D equals 3. Something like that. So you see that proving the existence of certain order phase is not that easy. But maybe we can, but I'll step back, we just use physics intuition to give a physics proof of these subjects, for example, in the time crystal. Yes?
How does one even go about doing these proofs? For example, the 2005, what went into it?
So I never looked at the paper, so I cannot tell you more than what I read from there. So
Okay.
you have to somehow take everything, like not restricting to lattices. I think there will be a reduction that you can first reduce to lattices, and then that will go.
Because with Merman Wagner, of course, you can show, by looking at fluctuations to show that the order gets killed.
Yeah, so it's easier to show there's no order than to show this order.
I thought actually the hard disk case is understood, but maybe not by Barry.
Yeah, it's not enough rigorous. So it's even in this case, it's not yet clear, I guess, to him that whether it's order or this.
He doesn't believe in the Costa-Rica transition. In other words.
Okay, so enough about the spatial crystal. I want to move on to time crystal. So you have the notion of spontaneous breaking of translation in space, but you could as well have that in time. So this was some study proposed and looked at by Wilczek earlier, and he was looking at spontaneous split breaking, continuous time in ground states. And he has a few papers on that, but it turns out that there is a follow-up paper by Watanabe and Oshikawa in 15 show that this is not possible in ground state and also in observable state, not in equilibrium. So this sort of prompt people to look into cases that you can evade these no-go theorem. For example, you look at non-equilibrium, like in periodic driving, and also look at, instead of continuous time translation, to look at discrete time translation. Okay, so let me just roughly define what I mean by time crystal. So roughly speaking, the rule, what I will be using will be the Floquet, but you could also consider Hamiltonian. Covering the underlying dynamics of a many-body system is time translation invariant, whether it's continuous or discrete, but the response from some local observable of the system spontaneously break that symmetry. It's like ground state. You have spontaneous symmetry breaking, you have all spin up, but it could also be all spin down, but you spontaneously choose one. And we would like time crystal to be robust against small perturbation interaction, and persistent, meaning that it can last sufficiently long. Of course, ideally, we would like it to be infinite. Like as your system goes to infinity, it should be infinite. But there are other manifestation of these time crystals that depend on certain parameter, but exponentially large. So just give you some phenomena in classical physics that you have these period doubling phenomena. So this is the so-called logistic map. It's a map of this. So R is restricted from 0 to 4, and X is from 0 to 1. And you put in some random number in this, and then you iterate and look at the fixed point. So in certain region, there's only one solution, one fixed point. But as R increases, you could have two fixed points. And then you have more, so there's like period doubling or quadrupling and more and more. And in physics, you have these Faraday's wave that if you have a liquid and you are driving it from below, then you can observe that the patterns can oscillate at half of the driving frequency. And this is actually related to the pendulum or the swing that kids play, or we also play at the start. The motion must be the palm motion. Like if you drive the swing, you can drive it by a motion which is twice as frequent, because there are different ways of driving, but that's one way. It's called parametric oscillations. So I just want to say there are already a lot of work on time crystals. I learned a lot from all these reviews. Of course, I don't claim I understand this. I understand some of it, but these are 3 very nice reviews. And so given the extended research, can there be anything new on time crystal? So I want to convey the message that's still new, something new. Even if you enter a field late, there's still something new that you can dig out. Okay, so this is the table from Els et al. I don't claim to understand everything here, but I will just show you that there are different ways of or characterization of time crystal. For example, this many-body localized discrete time crystal, pre-thermal discrete time crystal, and many others. So this is the one that I'm going to focus in the beginning as an illustration, and then move on to our construction. And I don't know where I will fit in, so could be an independent item here. Okay, so this is the outline. So I'm going to talk to you about these NBL discrete time crystal using the random Ising model to illustrate the period doubling. This is really a review of the literature. And then I'll move on to the construction of the period, which is not just doubling, but it can be any integer. And then we'll look at transition between 2, where you have n1 and n2, and you want to consider some kind of phase transition between them. And this leads to the subspace-thermal time crystal phenomena that I mentioned earlier. Okay. So actually, to get period doubling is not that difficult, right? So imagine you have spin, and what the action is doing is just flip the spin from up to down. You always flip, right? So discrete time 1, I flip. Discrete time 2, I flip. So response, of course, is doubling, right? So it's not that difficult to understand the phenomena of period doubling, but it's harder to show that it's stable against interaction perturbation. Okay, so I will explain more detail next. But can we go beyond period doubling? So of course you can. For example, instead of up and down, the spin could have n components, or you could just use a Zn clock model, and then collectively the spin could be 0, and then flip next period become 1, and then 2, 3, 4, up to n, etc. So this is a straightforward generalization of the Ising model. But then you can ask the question how you can actually study the interface of two different time crystals, and you want to look at the transition. So that probably would not be possible using a Zn, because then you have to couple to another Zn prime model. And then the more important question is, can these time crystals be stable? Okay, so this is what I'm going to show you using a specific model. Yes?
Oh, I guess we're on. Yeah. Does this require any nonlinearity in the Hamiltonian that's controlling the dynamics?
So what do you mean by nonlinear? You mean like density square or something like that?
Yeah, something that's just not linear.
So we would have interaction, like spin-spin interaction. There will be like Ising interaction.
Okay. So it's right away it's happening.
Yeah.
And then how would you physically flip a spin one way?
So
and
you
then the
have,
other way?
for example, magnetic field to drive it.
Okay.
Yeah.
Okay.
With some, you could use a continuous time, but then you only observe at a discrete time. After, we call it Rabi oscillation. Okay, so this is the prototypical model that has period doubling. So let me just maybe look at the first. For example, you use sigma x to flip. And then this is actually, Jim, this is how you flip, is you have a magnetic field in the x direction, right? And with certain time, it will precess. Yeah. And you are considering the time roughly is so-called pi pulse, where it flipped from up to down. This is the first segment of your discrete time evolution. The second segment is you put in any interaction. So you have Ising interaction, longitudinal field, transverse field, right? And here the time need not be exact duration that you flip exactly. So what I mean is, for example, you look at t equal to pi over 2, this corresponding to flipping up to down exactly, right? So, and you see that this, of course, this up goes down, down goes up. So you have these periodic doubling pattern. But then the question is, if you have these other terms that has interactions, that has external field, or even the timing, the T1 is not exactly pi over 2, would this be stable? So that's the question that one need to address. Okay, so they call this MBL because these couplings and external field are random enough. So they have many body localization. And this is the reason people usually quote to evade the thermalization, because you have MBL is stable under driving to infinite temperature. Okay, so we're going to look at this. We're going to look at the system at discrete time. So one period is t, and we're going to look at the system's response at n and see whether it exhibits any response. Like you can measure the spin polarization to see if up, down, these kind of flipping. And with these couplings and external field. Okay, so let's look at the extreme limit where t is pi over 2, and there's no, yes?
On like the spatial size of your system in order to kind of talk about this time crystal thing. Because if I imagine that if I have like a finite system, I'm just
Yeah.
Rabi driving constant.
Yeah.
Then I will always.
Yeah.
So, but you said that you have to use this MBL system. This MBL Hamiltonian to get my strain on like the spatial size or dimension.
So we want the system to be in the thermodynamic limit. You know, yeah.
So essentially you're saying that finite driving to the system. The driving. System it doesn't like dissipate.
There are other systems that the other cases you can consider coupling to the environment with the dissipation. Yeah. So here we're talking about closed system, but you will have external drive. Yeah. Thank you. Okay. So yeah, so let's look at the simplest case, and this is exactly solvable case where you have these pi over 2. So the first period, the driving, you evolve this, is really just flipping, so up to down, or any configuration, flip to its opposite. And then you have these transverse field equal to 0. So the second term only induce phases among the spins. Right? So even though this is interaction, but only induce phase. So in this case, you can solve that. For example, you start with any configuration. You know the next instance, it flipped to down configuration, right? And then adding some phases, right? And you keep doing it, still flipping and then adding phases. Yeah. So then this actually become a two-dimensional problem. The spin configuration is opposite. So you will write S and then the minus S. And in fact, it's really 2x2 matrix. 2x2 matrix, which just looks like X operator, because you only couple the up, up, down to down, down, up, right? And the 2x2 matrix is almost like poly sigma X, and then just stressed by some phases. You can diagonalize exactly. Yes.
If you speak up, actually, there is actually in the room.
Yeah.
Otherwise,
Okay, I'll speak, okay.
do some exercise.
Exercise your lung.
Fine, I can start the exercises here. Now, is it a feature of the time evolution operator, or does it matter what, like here you've picked the ground state?
It's another
So
ground. Not,
that size 0, does it have to be a ground state
oh,
there?
so we're considering that size 0 is any initial state,
So I could
product state.
start with any initial state
Yeah.
and then that everything would
Yeah.
flip over?
Yeah.
Yeah, okay.
Yeah, but you can think in terms of the classical state,
Yeah.
up, down, so it's easier to think about.
Okay.
Yeah. Oh. I don't know why this show up. Oh, this is not on my computer. This is on this computer. I just, yeah, turn it off. Okay, so this case is 2x2. It's really just coupling this to that. And then this second term here just induce a phase. So it's like 2x2 matrix. So 0, a phase, and a conjugate phase, and 1. And sorry, 0. And you can diagonalize exactly. So it turns out that you are familiar with this 2x2 problem. And the eigenvalue are +1 and -1 up to a phase. Right. So this is what I say here, up to a plus minus sign. So this eigenvalue in terms of phase is separated by pi. And the eigenstates are these cast states. These are entangled states. So any spin configuration and its negative one, it's conjugated or flipped one. So it's important that the eigenstate has to be a cast state. And so that any product state is like double well. If you have this well and that well, and they are coupled, the particle occupation would oscillate between the two wells. So basically, that's this kind of motion. But this is the solvable limit. So you can ask, what if I turn on these interaction, even if the timing is not right, right? If it's not exactly pi over 2, usually if you think of Rabi oscillation, if the timing is not pi over 2, your period would drift according to your external field. The strength would it depends on the strength. So then you can look at the numerics that they have done, this paper by Alves and collaborator. They are measuring, for example, sigma z, also xy as well. But in this case, we know the sigma z is the one that would show these period doubling. So you see that this really go up and down, and it's quite stable. This is the numerics. They use this as the initial state. So you see there's including these interactions, external field, this oscillation is still robust. And if you do a Fourier transform, the peak is at half the frequency. Yeah, so this is stable against local perturbations. And this pi over pi separation of the phase is robust. So this is the reason why the time crystal behavior is robust. And in more detail, they invoke the MBL and another assumption that's called local perturbation perturbed locally. So I want to maybe pause to see if any questions. Next page, I'm going to quote what they mean by this. So they say the time crystal is stable so long as a reasonable but non-trivial assumption about resonances. So they invoke the MBL, and they say that the energy of state that differ locally, there always an energy difference. So if you do the perturbation, you can only connect a state to its locally different state. And this perturbation, because there's a denominator non-zero, so this would only induce close nearby configuration. So if configuration that differ from O up to O down, things like that, they are too far away to connect. So these kind of cast states in the eigenstate of the Floquet operator is robust. And they say the unitary, local unitary, that cannot possibly connect short range states with long range entangled states. So therefore, this is robust. So that's their argument. So, but okay, so maybe in a naive way is saying that what this here says that if you do perturbation, you can only connect locally. So you only have some local flip. And as long as a distance, for example, you can define something called Hamming distance. It's really measuring how many bits are flipped. The longer the distance, the smaller the coefficient is. And meaning that if you start an entangled state, this roughly will be an entangled state. You cannot disentangle that under this. Okay. Any question on this? So this is reviewing the existing work.
I have a comment.
Yeah.
So it assumes essentially that you're only acting locally. It's essential that
Essentially,
the action of these operators is local,
yeah.
because otherwise this is not true. Okay.
Yeah, so this is they rely on many-body localization. So if you
And in the thermodynamic limit as well.
and some other, yeah.
Okay.
So but there are some debates about whether this MBO exists in higher dimensions. So
it's analogous to the stability of the spontaneously broken state.
yeah,
In the thermodynamic limit, it's a similar argument.
yeah, I think it's similar because this is you can interpret that this is special temporal order that Stony and collaborator proposed these kind of notion. Yeah. Okay, so I want to show you that people have already implemented the idea of time crystal, and they separate into 3 segments. In this example, this is on ions, and you see these oscillations. Of course, experimental results are not as good as numerical simulation. You see these decay. But if you Fourier transform the frequency, response of frequency exactly as half of the driving. And you also see this in NV, center and diamonds, although they have long range interaction. Right? So these have long range. So they may already evade the NBL. And you see the similar oscillation. I didn't show there. Fourier transform is basically the same. And more recently, you can actually implement this on superconducting qubits. For example, this is Google's machine. They see these kind of oscillations and really exhibit these period doubling. And another one is IBM's quantum computer. We're actually motivated by these experiments, and we want to design a system which shows period tripling. So instead of at 0.5, we want to at 1/3. So it's in that motivation that we try to find models. So yeah, so also we want to see if there any, well, actually my student went one step and become more ambitious and ask, is there anything new in time crystal? Right, so we want to construct general n period tupling. And we also want to realign these on the same system with different periods. And then we can ask, is there a phase transition? How do we even consider the phase transition between different time crystals? So if you want to realign this kind of transition, it's better to be on the same uniform platform, right? So you cannot take Zn and Zn prime, and there might be different spin magnitude. So it would be ideally to be on, for example, qubit system. And also, you have seen that one example, they realize this MBL. Can we not use MBL? There's also other proposal you see in the diagram earlier, they use pre-thermal and others. But can we have a discrete time crystal without many-body localization or pre-thermal phase? I didn't explain what pre-thermal phase, but you can ask me later. Okay, so these are motivations. So, okay. So I'm going to move on to the construction of ours, but I want to show first a similar work that they somehow have a similar idea of doing this by using swapping, and they call this paper, they call this swapping Floquet time crystal. So what they do is actually the second diagram here. The first diagram is what we just talked about, use flip up to down, and you could also do the swap. When you swap pairwise, then you swap back, you have a period doubling, right? So this is a very, very natural construction. And how you introduce swap is using Heisenberg interaction. So you can see Heisenberg interaction evolve in certain time will give you the swap, called the swap gate. So I just use the diagram, this I goes here, J goes there. So the Hamiltonian they have, essentially it has these swap operator or Heisenberg interaction, and then other interactions, random interaction, random field. And so that's not that important. Is the reason you want to have random coefficient of the coupling is that you want to randomize the state. So you don't want to have some local resonances like in MBL case. So you want the perturbation to be converged. Yes. MBL, so MBL you have only nearest or local, like near short range interaction. And here they do have polynomial decay. Yeah. It's not we trying to overcome issues, it's like we found that the model, also people have other, like long range interaction is not really an issue. Yeah. So like the experimental demonstration, these naturally has long range interaction in these ions, right? And also in these MV diamond center, they have long range interaction. Yeah. And in MBL, if you have longer range interaction like that, then you break the MBL. So it's no longer many body localized. Okay. So yeah, just want to show you that they show that if you still start with the nil state, and then the system evolve, and you still have these period doubling. So they just put -1 to the t, so you see that it's stay plateau for a certain time, and then it's stable in the sense that as you increase the system size, this take longer and longer. Okay. This is just numerics. Of course, there's an argument about it's stable, would have to invoke these local perturbation perturb locally. Okay, so with that, I want to introduce our model. The Hamiltonian is written down using Heisenberg interaction. But to write down is kind of ugly, but I'm going to use graphical later, graphical way. So I have H1 and H2. H1 basically swap 1, 2, 3, 4, for example, like that. And then H2 is swap, so you swap the R bond and you swap the even bond. So we divide into n to even and r. So this is not that important. So the detail is not important. The picture is this. So it's just hand-drawn pictures are not quite good. So basically, when n equal to 2, we want to construct period 2. We just swap as the previous case, 1, 2, 3, 4 swapping. So this represents Heisenberg interaction. N equal to 4, you have 2 layers. One is doing the n equal to 2 swapping, and then you do another swapping with 2 and 3, etc. And you see that I have n equal to 2 as a unit. So essentially, these terms with the minus sign is just canceling out those that cut across the boundary. So also n equal to 3 here, you have these kind of swap between 1, 2, 5, 6, and then the next layer 2, 3, 4, 5. And anything that cut across n unit sites that I would just drop the interaction. Okay, so this is the construction, but it's kind of writing down is ugly. This is the main swapping part, but you also need to add randomness to that, which is the kind of MBL-like interaction. But this can be long range, longer range, power law, or a longer range within the unit of n sites. Okay, so maybe I want to use the next picture to illustrate this. So n equal to 2, even though this is easy to see, is n equal to 2. So this box representing the Heisenberg interaction evolve in the proper time so that it realizes the swap. It is n equal to 3 is easy to see. For example, this spin gets swapped to here, and the next layer of gate is swapped to here. So this takes one step, and then the second time unit, this will start here and swap here. And then the third time unit, this will swap back. So you can check, this is really period 3. So we're just constructing this. And period 4, you can also check that this is a period 4. So basically, within each unit of n, this is already n period. So the configuration would swap from the initial to the final after 4 steps will be the same. Okay, so that's the construction. However, if you have spin that are the same, actually the period can be smaller because these may be identical, even swapping. Yeah. Okay, so and I want to point it out that even for different ends, the Hamiltonian pattern looks compatible, right? So from this, we can actually study the transition. Okay, so what we do now is we analyze the unperturbed case. So unperturbed case, I mean, for example, we think about the time is exact. So the first 2 parts implement the swap. And then the third one, implementing only the phase, only adding the phase. Just like the previous example that I showed you for the Ising case. So since we consider this is just not changing, not flipping, so the x direction is 0, so the second step only adding a phase. So this is really like generalization of poly x to n levels, okay? So this is just a remark that the spin can return, the spin configuration can return to itself sooner if the k is a divisor of n for configuration that are identical. For example, all spin are the same, the period is 1. Okay. Okay, so you can actually solve this exact case. So really, you start with some configuration Zm, it flips to the next configuration with a phase. And then after n period, it come back. So this really like n by n shift matrix. So for example, the 3 is this case. But with the second turn, giving the phase, it would just modify. So for example, like that. And you can solve this, the eigenstate and the eigenenergy, quasi-eigenenergy. And the important point is this part. Is 2 pi over n separation for the quasi-energy. Right? And this is actually easy to see if you understand this is just a poly matrix, generalized poly matrix, always has these, when you diagonalize, would have these root of unity, nth root of unity. And therefore, their separation is 2 pi over n. So what we need to do to show that the MBL, sorry, not MBL, the time crystal behavior of n period is robust, we need to show that this spectral separation is robust against any perturbation. For example, adding these epsilons and then changing the timing, even reduce it, not exactly being the swap. Okay. Sorry, just flip too quickly. So maybe in the interest of time, I will skip this symmetry. So you can actually generalize. You find the operator S which commute with your Floquet operator. That's signifying that this is a symmetry. But this is our trivial. But the more non-trivial thing is when you restrict to the subspace with alpha, meaning that these are the n configuration that are connected by these swapping. This is proportional to this up to a phase. Okay. And so then you can ask, how do we observe these end period response? So you can show that this spin under that course would return to itself after n step of Floquet. You can measure this, but you can also measure a Fourier transform of that. So you can measure the Fourier transform of that. So what we do is you look at the sigma and it gets transformed to the next time and then next time, and you can do the Fourier transform. So what I mean is here, for example, n equal to 4, this 1 would get moved to 4, would move to 2, sorry. This special one here is actually moved to 2, and then 2 will move to 3, 3 move to 4, like label in this red. So I'm going to do a Fourier transform. I'm going to add this time step 1 to have this phase factor. Time step 2 has e to the twice the phase factor, 3, etc. It's really doing the Fourier transform in time. Okay, so you can also consider this. This will be the observable that we're going to evaluate. And so let me just introduce, this is the Fourier transform. And so under each Floquet operator, it induces a e to the 2 pi over n phase. So this is essentially the object we're going to measure. So what we do is we start with many configurations and we measure its time evolve and normalize at the 0 time. And we take the argument will be the phase. Right? And you see that this is the disorder average. So here I argue for the exact case, but in the numerics, we add a lot of impurities, randomness, and you see that for L equal to 4, 8, 12, this become longer, it's more robust as the L go bigger. And you do see the period 4 from here to here. Essentially, this is the cosine of the angle here. So you do see the period 4. 1, 2, 3, 4, etc. And if you do the Fourier transform of this A, you see a peak at a quarter of that driving frequency. So this is a disorder average and with interaction. So this show, the numeric show is robust. Yeah. Similar to the previous case of the icing. So how do we show that's really robust from a theoretical analysis? So to do this, we need to introduce a formalism that allows us to do perturbation. So this is your Floquet, and this is your, with perturbation, this is the Floquet with additional V acting on that. Yes? It's the system size. So yeah, system size. So here, this is showing as you increase the system size, this persists for a longer time. and hopefully it should be exponentially longer. And in the thermodynamic limit is stable. Okay, so I want to mention that we developed a perturbation theory to analyze that. And we show that this 2 pi n spectral separation is perturbed up to, roughly lambda. Lambda is the perturbation strength. Alpha, in this case, we have 4. Here, n equal to 4 will be L equal to 4. So this is exponentially small as the system size increases. And I show you the numerics. So just focus on these 3 plots. So we see the perturbation, this deviation from 2 pi over n. And you see that L equal to 4 is scaled with lambda equal to 1, L equal to a, scale with lambda squared, and this scale with lambda to cube. And this is consistent with our perturbation. So I don't have time to go through the detail of perturbation theory, but you can actually argue that. So here we rely on a weaker notion of this local perturbation perturbed locally. So maybe let me not go through the detail here, just give you the naive picture. So remember the local perturbation perturbed locally is that even for smaller term, this decay exponentially. So what we require is that we only look at the separation, which is greater than some macroscopic size of the system. If it's greater than that, we ignore that. But we don't need to care whether this is small or not. So this is what we call local perturbation cannot perturb globally. Okay, so this allows us to show also the cast state remain cast state. So cannot be turned to an unentangled state. So so this is just to remind the previous argument for local perturbation perturbed locally. Okay, so let me also skip, since I didn't talk about symmetry too much, and also the emergent symmetry, I will skip that. So maybe with remaining 10 minutes, I will talk about the transition between the two. So how do you consider phase transition between two tight crystals with 2 different periods? So for example, you have this n equal to 2, n equal to 4. Remember, you have these interaction, Heisenberg interaction, right? And for n equal to 2 and you have n equal to 4, you have additional term. So to consider the phase transition, usually in the equilibrium, we can sort of do interpolation from one Hamiltonian to another one with linear interpolation. So this is exactly what we're going to do here. So we have these N1 driving this. We have N2 driving this 4 period. We just do the linear interpolation. And then we let them evolve with this interpolated Hamiltonian for the corresponding time segment. Okay. Yes. Yeah. So we are already constructing, for example, we have n equal to 2, or we already specify what kind of period we want. So you mean this logistic map in the beginning? Yeah. But there's also a control parameter. This is the R. It controls the regime where you have 2 or 4, etc. Right? Right. But there's still this tuning parameter. Yeah. But here we already laid down the structure for it to be n equal to 4. But if you consider this n equal to 2, n equal to 4, if you mix it, then it's hard to say. So maybe it stay n equal to 2. That would be the natural guess. So maybe extending your thought, maybe one could consider a random, like you have random units. and then you mix them and see what spontaneously would give rise. Yeah. Okay, but the setup is simple. You just interpolate them and you look at the Floquet. And then you could also look at all those poly sigma z's that would transform from one side to another, a time step to another, and then you group them together. So I didn't talk about the detailed construction of this, but this will be the conserved charge that we refer to. So, and we show that, of course, these conserved charge can be shifted to the next one. So then with this, you can actually diagonalize similarly to the previous construction. If you know the response is periodic in the exact case, then you can diagonalize and look at the eigenstates and eigenvalue, etc. Now, if you start with some kind of configuration, like classical configuration, they would have definite z conserved quantity, and they can be written as a superposition of all those fragmented segments that have the same charge. And after n period ng, so ng here is the greatest common divisor of n1 and n2. After that, it will induce this phase. And if you consider a multiple of ng step, this will induce phase here. And if this phase is random enough, this will become a thermalized, right? This will be equivalent to thermalized phase in the subspace where you have definite charge. But this, in order to see whether this will lead to thermalization, you need to look at the level statistics. So this is what I'm going to show next, is numerics. So essentially, the picture is that if you increase the S, and so that the level is random enough, is fit into thermalized phase level, then you can have subspace thermalization. Yes, okay, yeah, I'm about to finish soon. Yeah, so this is the numerics we do. So in order to look at whether it's really thermalized or not, you look at this so-called level statistics using the gap ratio. So I won't say too much on this. I think there are a lot of background. This is also introduced in many body localization. They use that to diagnose what phase is that. But what you can see is that you see the numerics as you increase the S. For small s, this is still Poisson. So this is still the discrete 2-period time crystal. And then as you increase, you see that this R goes up to 0.53. It's in the circular orthogonal ensemble. This is thermalized. So circular because we consider Floquet, the phase is mod 2 pi. Right, so, and you see as you approach to n equal to 4 time crystal, it goes back to the Poisson. So there is a subspace thermal phase here. And if you look at the response, of this quantity that I defined earlier, you still see this is actually periodic. It's actually period 2. So up, down, and the period, you do the Fourier transform, this is half the frequency of the drive. So this shows that there is a subspace thermalization, and there's also discrete time crystal behavior. So this is, I guess, the last one. Last one, the stability we can analyze using the perturbation theory, and the scaling is similar to the previous case. Okay. So maybe let me conclude. So we constructed a spin chain that allow us to have n-tuple discrete time crystal. And we studied the phase transition between the two. This is the last topic that I rushed through. But we found a new phase of matter which has a thermalization in subspace that has a definite charge. And it exhibits spontaneous symmetry breaking in time. So we call this subspace-thermal discrete time crystal. And I want to emphasize this cannot happen in MBL because MBL many body localization is really incompatible with thermalization. It's also not fully thermalized. So we introduced a new perturbation framework. I didn't have time to go to the detail. The proof is relaxing the previous condition. And we don't see any requirement of MBL. So this can also generate to higher spatial dimension, higher spin. You might be able to consider the two-dimensional discrete time crystal. And we think this is possible to implement in the current cloud-based quantum computers. So I guess that's it. Thank you very much.
We have time for a few questions. I have a quick one.
Yes.
Is there any universality associated with the space transitions?
That's a good question. So we did found an exponent, the critical exponent correlation length. From here, I think it's about 0.6 something, but we only have one exponent, so we cannot.
So is there any interpretation for what the exponent means in this case?
At this point, we don't have,
Okay.
but yeah, but this would be a very important question to ask if we want to identify universality of the transition.
Okay. Just pick up, I think the room has.
So you talked to show that the system has got kind of sub-harmonic response that is
Yeah.
robust to perturbation. I could also say it's robust to some unique details of your model, right? So is it possible to establish a coarse-grained effective theory that captures the sub-harmonic response?
Coarse-grained theory. You mean some kind of field theory description or that I don't know people have developed these kind of field theory. I mean, Wilczek has these Lagrangian way of looking at continuous time crystal, but I don't know this discrete time crystal. People have looked into the field theory description. Do you know?
I don't know.
Maybe that's something for you to dig into.
It's a homework for you.
Crossover to an angle for the discrete time crystal. You said this is in the absence of MBL. Is this some pre-thermal?
It's not pre-thermal. So usually the pre-thermal is you have external drive, which is driving very fast. We don't have a time scale that is fast. So this is not, we just apply the gate. So we don't know where we put our result into that diagram that I show you. I think it's not MBL. It's also not pre-thermal. Yeah.
Another question? Another answer? Okay, let's thank Chieh.
Thank you.